So we're still on our journey here talking about how we're going to run into things that are polar and non-polar in cosmetics and they're going to mix. We also talked a little bit about oils and how a lot of cosmetics try to address oils, right? They're trying to get rid of oils or add oils. And so it's really helpful to know what will mix with oils. And so previously, what we talked about were bonds, covalent bonds that were polar or nonpolar. And we said, hey, look, nonpolar bonds are going to be things that have the same atom because they have the same electronegativity. Or they are going to, right, have an electronegativity difference that is less than 0.5. So to determine, so those are all bonds. And now we're going to kind of shift and talk about molecules because bonds are just parts of molecules. And so we're going to look at molecules here. So to determine if small molecules are polar or nonpolar, we really need to look at their shape, okay? And if a molecule is completely symmetric, it will be nonpolar. So I want to review a few things. Molecules can be polar or nonpolar. Okay, we can put them into those two categories. A polar molecule, like what we talked about on the previous slide, has an uneven distribution of electrons over the molecule, while a nonpolar molecule has an even distribution of electrons. Now, for molecules that only have two atoms connected by a covalent bond, the polarity of the molecule is the polarity of the bond, right? And that's just determined from the electronegativity. Now, when a molecule is composed of three or more atoms connected by several bonds, we have to consider both the electronegativity of the atoms that are involved and the shape of the molecule. Okay, so when we look at shape is tricky, and we're going to build some of these in class. But when we look at shape here, and we're looking at this particular molecule, we have a carbon and it has 4 hydrogens attached. Because this is a two-dimensional surface, it looks like each of these angles, which would be the distance from this hydrogen to this hydrogen, are 90 degrees. In reality, molecules are three-dimensional. And so what we find is if we've got this carbon bonded to 4 hydrogens here, then the distance from this molecule to this molecule will be 109.5 degrees. So there's a considerable difference there. Now, you're going to run into a couple different shapes, and we're going to talk about whether these are polar or non-polar. When we talk about symmetry, if you have a central atom and it is surrounded by 4 of the same molecule, that is symmetric and will be nonpolar. Okay, so let's write that down. Okay, if a central atom, and I'm going to adjust it just a little bit because I want you to have it written down, has no lone pairs and is surrounded, and I'm going to say is attached to the same atom, it's nonpolar, right? So this is carbon and hydrogen. We've already talked about carbon and hydrogen being nonpolar anyway. So I want us to look at CBr4. CBr4 is a central atom with surrounded by 1, 2, 3, 4 of the same things here. Now, I want to point something out. Carbon to bromine here, this is a polar bond because there's a difference in electronegativity. But because all of these polar bonds are the same, that means they're all pulling the same amount of electrons away from carbon. then it becomes nonpolar. So this molecule here is nonpolar, right? View it like a tug of war where these are all pulling the same amount, okay? So let's look at some other molecules and let's put some words to kind of some of these shapes, okay? So we talk about these molecular shapes and how they matter. So if we look at, for example, carbon dioxide and water, okay, and when we look at carbon dioxide here, we have two polar bonds. So this is a polar bond and this is a polar bond. But because this is a linear molecule, each of these are being pulled equally. So the electrons are being pulled equally in this direction and equally in that direction. And you can see that shown here. And so what that means is that is going to be nonpolar. Okay. Now, let's contrast that with water. Water is a bent molecule. And so what that means is it's got two hydrogens here with two lone pairs here. And so the overall shape of it is bent. And so when we look at this, what you see is that the electrons are pulled in this direction and in this direction, and so it ends up being a polar molecule. Now, these two molecules look strikingly similar, except they do have what we call different shapes or different geometries. CO2 is linear, whereas water has a bent shape. And those shapes lead us to figure out, hey, look, is that going to be nonpolar or is that going to be polar? So knowing the molecular shape really helps us determine whether a molecule is polar or nonpolar. So how do we go about predicting shape? Well, we use valence shell electron pair repulsion theory or model, and that's a mouthful. So we shorten that to VESPER. And basically what this says is that electron groups in the valence shell, now we know the valence shell from the previous module, that's the outermost shell of the atom, and that's the one that's involved in bonding, will arrange themselves as far away from each other as possible. And that leads to the geometry, right? So we've got these electron groups. They repel each other. They want to get as far away from each other as possible. And so that results in the geometries that we're going to talk about. Now, it's worth pointing out that when I talk about electron groups here, okay, these are either bonds, right? So bonded electrons or lone pair electrons. Now we are going to look at some examples on the next slide of what these structures are. Okay, so let's start here and let's look at the structure that we've kind of looked at before with CH4. We have carbon and we have 4 hydrogens here. When you look at this, you have a central atom and it is connected to 4 things. So this is connected to 4 other atoms. Okay. And it has no lone pair electrons. So I'm going to say LP electrons for lone pair electrons. The shape of this molecule is called tetrahedral. Tetra is, the tetra prefix there stands for 4. The reason this is called tetrahedral is because it has 4 faces. So if we look here, we have one face here, one face here to the side. There's a face kind of here on the other side, and then a face on the bottom. And that's where we get that tetrahedral from. So it's got 4 sides there. The bond angle for this tetrahedral is 109.5. So that would be measuring from here to here would give us 109.5. Okay. Now, sometimes we are going to have molecules that have 4 groups around them, but they're not bonds. Sometimes they are lone pair electrons. So this is an example of, it's called pyramidal here, but I'm going to change it to a little bit different word. It's actually trigonal pyramidal. When we look at this, what we see, right, is that we've got these lone pair electrons here, and they are going to take up space. And then we see 3 bonded atoms. So we have trigonal pyramidal. We are going to have 3 bonded atoms and 1 lone pair of electrons. Now, here's something that's kind of interesting here. These lone pairs, they take up more room than if they were bonded. And so what that means then is they squeeze these atoms here closer together. And so we find that their bond angle is less than 109.5. Okay, so the distance from here to here is less than 109.5. So that's trigonal pyramidal. The third shape that we can have that still has 4 groups is linear. In this one, we have 2 bonded atoms and 2 lone pairs. And I just said linear, and it's actually bent. Right? So when we look at this, we've got a central atom, 2 lone pairs, 2 bonded atoms here. These lone pairs take up more room than if they were bonded. So then this bond angle here is less than 109.5. So these are kind of 3 molecules that we'll see where we have 4 groups around them. The other 2 that we'll see where we have a central atom, one will only have 3 groups around it. So it has 3 bonded atoms. And that's trigonal planar. And then we will see one that is linear, where it's got a central atom attached to 2 things. Sometimes this will look like just 2 atoms that are attached as well. Okay, so you've got kind of two choices here for linear. This bond angle is 180. So I wanted to show you with kind of the faces here. All right, there's a lone pair. This says 107 for the bond angle. 107 is fine, but what I'm really looking for here is just less than 109.5. That bond angle will vary depending on the atoms that are attached, right? So all I want you to know really is that if you've got lone pairs, it's going to be less than 109.5. That's it. But this kind of helps us visualize these 3 here so we can see those. So we're going to use VSEPR and determine the shape of each molecule and then help use the shape to figure out if it's polar or nonpolar. Okay. So we're going to start here with SiO2. This is silica dioxide. When we look at this, we're looking right here at this central atom. We see that it's a central atom and it has 2 groups. It's got one big group here and one big group here. Okay. So because it only has 2 groups, it is linear. The bond angle there would be 180, right? And because this group and this group are the same, that means they're going to pull the same amount of electrons off silica this way or this way, and that ends up being nonpolar. Okay. Now, let's look at the next example. This is H2S, right? We're looking here at this central atom. And when we look at the central atom, which is sulfur, we see there's 4 groups. There's 2 lone pairs here, then it's bonded to hydrogen here and bonded to hydrogen here. Because it has those 2 lone pairs, we know that, hey, look, this is bent, okay? And the way it would really arrange itself would look more like this, okay? And what happens here, right, is that we would see, just like with water, the dipole moving towards sulfur. And so that indicates to us it's polar. All right, now let's look at our last one here, which is PBr3. When we look at PBr3, we see that it has 4 groups, 1, 2, 3, and then 4 here with those lone pair electrons. So that's 3 bonded atoms and 1 lone pair electron. So that means it is trigonal, pyramidal, right? And it is also going to be polar. Now, I'm going to tell you a shortcut with these small molecules. If there is a lone pair on the central atom of a small molecule, and all we've been doing, we're going to talk about big molecules in a second, all we've been doing is small molecules, then it's polar, right, for what we're going to see. So you'll notice here, there's lone pairs here, that's polar. There's a lone pair here, that's polar. For these small molecules, that's how we're going to figure out that they're polar a lot of times, or something else we can look for. Now, I want to take a moment, though, and talk about the polarity of larger molecules, because you can't use that with larger molecules. A few things about larger molecules. A lot of larger molecules are going to contain carbon. We're made out of large carbon molecules. And so we are going to begin to talk about that as we get into the different carbon molecules that are in cosmetics. Carbons can either make single, double, or triple bonds. And so just based on carbon, when we see here, the carbons we're going to see are not going to have any lone pairs on them. You will only see their molecular shape as being tetrahedral, trigonal, planar, or linear. Okay, so those are the 3 we're going to see with carbon. With oxygens, if you see an oxygen, right, that's just out, our oxygens will have 2 lone pairs on them most of the time. And so you're going to see there. So when you have a larger molecule like this, and you are looking at the geometry, you will be asked to look at the geometry of a particular atom. So for example, for this carbon, there's 1, 2, 3, 4 groups attached with no lone pairs. Is tetrahedral. Same thing with this one. This oxygen is bent because we have a central atom. There are 2 groups here and 2 lone pairs there, and it is bent. And so that's what we see there. So for larger molecules, you have to look at specific atoms. Now, I want to talk about the polarity of larger molecules. This a lot of times depends on the structure. Every time it's going to depend on the structure when we talk about the polarity of larger molecules. And so we're going to have a general rule. Generally, if there are 4 carbons per electronegative atom, which most of the time is going to be oxygen for us, or less, it's polar. So, for example, let's say we have this molecule. It's got CH3, CH2, 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 OH. We're going to count the carbons. There's 1, 2, 3, 4, 5, 6, 7 carbons. 7 carbons per 1 oxygen. So that means that there's so many carbons that it's going to make this nonpolar, right? It's more than 4 carbons per oxygen. However, if we compare it to ethanol, which is this molecule, there's 2 carbons per every 1 oxygen. And so that tells us it's polar. So this is one of the ways that we can help us identify these larger molecules, if they're going to be polar or non-polar. So hopefully after you've listened to these 2 screencasts, you have a lot better grasp of being able to identify polar and nonpolar molecules. Um, in the next screencast, we are going to kind of dig around and see why polar and nonpolar molecules do not mix.